So we're now ready to learn the technique of factoring by completing the square. Before we start, let me just tell you that there are many different ways to complete the square. The technique that I'm going to present to you happens to be my favorite technique, but I'm not saying this is the only way. Also, we're going to see more and more difficult situations. We're starting with a really easy case at first. The first thing that you need to do is make sure that your quadratic trinomial is arranged by degrees. So first the highest degree, then the lower degree, then the number term. That is, in this case, that is done for us. The second thing, very important, you have to make sure that the leading coefficient is 1. So the leading coefficient is the number multiplying the variables in the highest degree term. So that's the number multiplying x squared, that is 1. So the leading coefficient is indeed 1, which means we can get started. So the first thing that we're going to do is find half of the linear coefficient. Half of the linear coefficient. So the linear means of degree 1. The linear term is negative 10x. The coefficient in that is the number multiplying the variables, and be careful, sign is included. So what is half of the linear coefficient in this case? It's half of negative 10, which is negative 5. Suppose this is your paper. And this is going to be your main computation. So before we even start the main computation, I want you to go away from here, go to the margin, and write down that magic number we just found. Half of the linear coefficient. So that's negative 5. And then we put an x in front of it. We put them in parentheses and square. This is not part of the main computation. That's why it should be put elsewhere. This complete square, x minus 5 squared, we're going to expand it. So this is x minus 5 times x minus 5. You remember that stuff. So we're going to end up with x squared minus 5x minus 5x plus 25. Or better yet, x minus 5 squared equals x squared minus 10x plus 25. This is what I call your helper line. Okay, so what happened here? We haven't started the main computation yet. But what happened, here is a complete square, x minus 5 squared, that when we expand, we find that the first term and the second term is exactly identical to the first and second terms of our expression. What this means is that if we want to factor this expression by completing the square, that means we're going to push this expression towards a complete square, and this is the one that will work. So basically, we want to manipulate this expression without changing its value so that it will look like a complete square. So we finally start the main computation. X squared minus 10x plus 21. Notice that I didn't do anything yet, right? I just left a little gap. So this line that I call your helper line, what are we missing for our complete square? How do we need to complete that square? We have x squared minus 10x, but we don't have the 25. So in order to complete the square, we have to somehow see a plus 25 there. So I'm going to add 25 here. But remember, we are not allowed to change the value of our expression. So I will immediately subtract 25. This technique is called smuggling. Basically, this is what I want, plus 25. This is the payoff because we can't just add 25 to our expression. At first it looks silly. You might say, well, but they will just cancel out and form a 0. That is true, but what happens is that they are not going to the same place. They will part ways. The first 3 terms are going to be absorbed in a complete square. So the second time you're using your helper line is when you recognize that, wait a minute, x squared minus 10x plus 25, x squared minus 10x plus 25 equals to x minus 5 squared. So the first three terms can be rewritten as a complete square. And then all you have to do is what's left, minus 25 and plus 21. You just have to combine those two numbers, and we get negative 4. Now, if someone says complete the square, you're done. This is what they want to see. But if someone says factor by completing the square, then you have a few more steps. We can rewrite this line as a difference of two squares, because 4 happens to be a perfect square, right? And now we can apply the difference of squares theorem. Basically, the difference of squares theorem states that a squared minus b squared is a plus b times a minus b. In this drama, we're going to cast the following characters. A will be played by x minus 5, and b will be played by 2. So if we repeat this line, but instead of a, we're going to say x minus 5, and instead of b, we say 2, then here we're going to have x minus 5 squared minus 2 squared, and here we're going to have x minus 5 plus 2 times x minus 5 minus 2. And so this is the big step, and you notice this was the difference of squares theorem. And now the only thing that is left for us to do is clean up by combining like terms. So we have x minus 3 times x minus 3. And until you're an expert, you should obviously check if our computation was correct. So when we multiply these two, we should get back this. We have x squared minus 7x and minus 3x combined to minus 10x, and minus 3 times minus 7 is plus 21. So our solution is correct.